one. The lab. Okay. Let me brief you the lab a little bit. It may take about 10 minutes. Okay, before we finish the class. We have the group 1 and group 2. We have the lab 10 and lab 11. Is going to be the direct shear. The first one is the direct shear for the matrix material, include brass, copper, aluminum, and that is going to be in the form of double shear. You know double shear, right? And next one, we have the wood. However, the wood, we're going to test it in the single shear and is in the parallel of grain. I first start by talking about the wood. Okay, the wood, when we go up the wood will go up, and then the wood will have the grain of the wood parallel to the height of the wood. If you cut the wood and then you draw the cross section of it, okay, and you will see the annealing of the wood. That's annealing count the edge of the tree, okay, and the wood mostly will cut in the region of this annealing and use it and call it in the technical term as the timber. So we have the course called steel and timber design. We didn't have the steel and wood design because timber is the engineering wood. Maybe we just call it timber is equal to the engineering wood. Okay, what's so called the engineering wood is we cut the wood and sell the wood in the form like this. When you cut this one, so most of the timber will come in the piece, something like this. And you have what? You have the grain that parallel to the length of the structural member. Okay, so when you use the wood, most of the time we will use the wood, the timber in the parallel to grain to resist the force. And I will have this discussion to this later because this parallel to grain is practically uses in our engineering application. So now we will test them for what? We will test them to determine the shear strength. So that means you're going to shear the metal by double shear test. We will shear the wood by the single shear. The test will be very simple. And we also will take a note on the mode of failure of the metal and the wood in our study. Okay? And what we have now is the basis knowledge of this. When we shear this metal, what we have by the test of this, we will have this specimen fail by these two portions. When you cut this portion and draw the shear diagram, you can see the shear force of this gonna be F divided by 2. And this shear force is the direct shear. So this form will produce the direct shear stress across the section, and we can determine the average shear stress by the shear force divided by the area that shear force act upon. Okay, this is the area there. And the direct shear has 3 types. One is single shear, the second is double shear, and the third is pure shear. In the lab, we will use these 2 kinds of shear in our study. And for the single shear, you may see we can the structure like this one by using the bow. And by using this bow, you can see if you separate this piece of steel by the force of F, you may see we have the hole that's our bow gonna be put into this. If the pace will be in equilibrium, we require the force here. The force here is the F will be over here. The force also on the bottom portion is going to be, let me put it in this color, in this direction. So this force by the third law of Newton will apply here. So the force that acts upon the bow will cut the bow one plane. So we call this as the single shear. And then we will have the cut show over here. See, this is the evidence that we have due to the failure of the single shear that may be occur in the bow. Okay, and this one is a single shear. So since V equal to F, see the shear force here equal to F. So the equation is the force divided by the A. And you may see this one in this clamp. And for the double shear, many times we use the double shear in engineering. Okay, again, you may draw the Fibonacci diagram of the plate. By doing this, we have what? We have the plate. If this one is F, the resistance force over here is going to be half of F. And again, we have what? We have the hole that's put into this. So to connect them together, we have the bow. And then to make the plate in balance, the force F over 2 will have the force F over 2 here. And it's going to act here. And then also we have the force F over 2 here, in which is going to act F over 2 here. And then the force F here require the resistance force F here. And the resistance F here is going to be in this sides of the bow, is going to be the F. So it's balanced. This is F over 2 plus F over 2 is going to be F. But this time the plane, the shear plane gonna be double like this. By using this one, the shear gonna be F over 2. Which one is to be this one, and then divided by A. Now the bow over here, is going to be the example of the bow that is in double shear. However, the bow over here, let's show here, this here is going to be in single shear. Okay, so the bow can be double shear and single shear. And at the same time, if you consider the timber, you may see by using this one, the failure plane of this timber are two failure plane here. So this time the timber is in double shear. So the wood or the metal, the wood and the metal can be both in the single shear or double shear, depending on the way we use this in our structure. Okay, come to the test. Let me start by the double shear of the metal. So the first step, Ajahn will have the metal specimen is maybe the brass, the copper, or maybe the aluminum. You use the vernier, measure the diameter of this one. So first one, you measure the diameter D, and then you find the D average. From the D average, you can find the average area of this one, And then the second one, I like you to weight specimen. And when you weight specimen, you also need to measure the length. Okay, you just compute the density of each specimen. It must be aluminum, brass, and copper. And you just divide the weight of aluminum by the volume of aluminum. I like you guys to determine this. This second step is the new one. We didn't do it for the previous one. And then the third step, okay, you need to come to this. You need to adjust the handle until the hole over here is clear. Okay, you just install the specimen. You just put this one into this. Okay, and then the force, you perform the test. This time you put the needle. You move this needle, the black and the red come together. Okay, and then you increase the load by rotate the handle slowly. And then what you can see is the needle will be increase. And then when it reaches the limit, okay, the black needle will separate from the red needle. And then you read the P maximum. And then the fifth, you take note on the failure of the specimen. Okay, you got to draw the picture of the specimen, and you can see the metal specimen. Part of this is going to be very clear. A portion of this very clear, and parts of this you will see some texture. Okay, you must draw this one. It's going to be the same for this three metal, and we make this discussion. And you're supposed to be understand that for the clearing portion, this is the way that's the metal cut by the testing fixture. Okay, but for this portion is the portion that the material failed immediately. You will still hear the sound click during its fail. Okay, and then for the wood, you will have the specimen in the form like this. You must measure all the dimension of the specimen, and then after you measure the specimen, then the second you weight it. And then you find the law of this by putting the weight divided by the volume. Most of the time, the specimen has higher density. They're supposed to have the higher strength because the higher density wood has more grain and can taking more loading. Okay, and then the third, you just install your specimen into this casing. Okay, and then you put all of them into the compression machine, and the specimen in this way is going to lock. Okay, by the steel casing is going to lock in this way. And then when you apply the force will transfer by the steel plate here. And then you just turn on the machine and increase the loading. So before increase the loading, just put up the peak recorder when it's increased the force and then to the max. Okay, the failure may occur usually since this grain is in this direction. Most of the time the crack will occur like this. Okay, and then the fourth step, you just notice the failure. Okay, and then you determine the area of the crack, and then you can find the tau equal to P max divided by the area. That is going to be very easy to determine. And what happened is sometimes the crack is not like this, sometimes it's cracked like this. If it's cracked like this, for example, is this one cracked like this, and the other one cracked in this way, we're going to measure the crack. Okay, you measure the crack. You measure the one in the light blue and do the average. Okay, let's see. This one going to be A1. This one going to be A2. So we have the A average equal to A1 plus A2 divided by 2. Again, you also have the B1, and this one is the B2, and you have the B average equal to B1 plus B2 divided by 2. And then the area that I just mentioned previously here will be compute equal to A average is going to be AVG, and then it's going to have B AVG. Okay, let's see, we have this, and then we will have the area divided by the maximum force, and then you can determine the ultimate of this. Okay, for double shear also, you can have this one, and then just divide the maximum force. This one will be tau equal to P max divided by 2, because this is double shear, and then divided by the A average. Okay, and then you may put this one just sketch. So you must sketch this one. You cannot take the picture. You must sketch the test setup, and you may record the testing result, and then you got to sketch the failure mode, and you do the discussion and conclusion. You take the picture, you make it as the PDF file, you set the name and turn it into the Google Classroom. Okay, that is for the metal. The next shear for the steel, sorry, it's not steel, it's brass and copper and aluminum. And this one for the wood, do the same thing. Okay, thank you very much. That is the end of this lecture. And we will have the online laboratory on Thursday. Hope you guys have a nice day and also be safe from the COVID.